Okay? Okay, so it looks something like this. Moving charges are one of two sources of magnetic fields. We have moving charges. Well, actually, there's three sources, but we'll get there. We have moving charges. We have permanent magnets, okay? And there's one other thing that causes magnetic fields, which we won't get to for another couple chapters, all right? But if you're moving along this line, you can see these are the magnetic field lines, okay? And then tangent to those lines are the magnetic field vectors. Just like with electric field lines and electric field vectors, okay, the vectors are just tangent to the lines at a particular point. And the density of your lines and the distance of your lines from your thing that is causing the lines tells you what the magnitude of that vector is. The lines give you the direction, and then you have to get the magnitude from something else. So, if you have a charge moving here, it has a magnetic field in all of space. We're only representing some of it with the lines. But you can see it's going to have a lot of, the magnetic field's going to be big here, right? So these are big vectors. And as you get farther away, it's going to get smaller. But if you go down over here, right here, exactly along this line, not much of a magnetic field because you're not perpendicular to the direction of motion. You're parallel. Okay? But if you go out a little ways, like over here, so if you're at some distance here to here, this would be your R. Okay? Your magnetic field is still perpendicular to the direction of motion, but it's smaller because it's farther away. Okay? You want to look at this front-wise. If this charge is going this way into the page, okay, you can do your right-hand rule. That means the charge is moving this way, so you can point them in the direction of current or in the velocity direction for a positive charge. Remember, this can get complicated because what else can we have? Negative charge. Okay? So in the velocity direction for a positive charge, and then you have these circles that go around your charge. Okay? Now, this gets real ugly when you start to try to draw out the math. Okay? So this is like thinking about this point right here. All right? So here's your direction of motion. Here's the point where you care about the magnetic field. Here's your distance between your charge, which is now moving, and the point at which you care about the magnetic field. That is still called R. Okay? Just like before, when we had an electric field, we had a charge, and we picked a distance between the charge and where we cared about the field, and we called that R. Okay? So here's R. We know the magnetic field, in this case, points sort of out of the page. Okay? Because it has to be perpendicular, this is the direction of motion, it has to be in this plane perpendicular to the direction of motion. Okay? So, in order to get this, you have to figure out what plane is formed by V and R. Okay? And then your magnetic field is going to be perpendicular to that plane. Everything is perpendicular to everything else, essentially. Okay? So what does that look like mathematically? Well, something like this. Okay? And this isn't the whole picture. As you can see, it's written like in two pieces, which means we can write this a lot cleaner in math. All right? But let's go through what the variables are that we're using. So this is the magnetic field at some distance r from your moving charge. Okay? Here is your charge, q. Okay? Here is your velocity, v, or in this case speed, because it's not treated as a vector in this format. Okay? This, theta, is the angle between vector v and vector r. So the angle in the previous slide, theta. Okay? This is the distance r, so from the charge to where we care about the field. All right, and it's squared. Remember we said this would probably be inverse squared. This is magnetic permeability. Okay, so it's like epsilon naught, but for magnetic fields. Okay, and we call it mu naught. Okay, that's the magnetic permeability in free space. And what do we mean by free space?
A vacuum.
Vacuum. Okay, so this is the magnetic permeability of a vacuum. Okay, and this is 4 pi. So it turns out this is useful because magnetic permeability is 4 pi times 10 to the negative 7th Tesla meters over amps. Okay, if we take this and divide it by 4 pi, what do we get? Yeah, 10 to the negative 7th. Okay? So this whole thing is just 1 times 10 to the negative 7th, or just 10 to the negative 7th. All right? Now, if you want to write this in a prettier mathematical way, it looks like this. Okay, so now let's go through what this is, and we'll talk about it a little more later. But here we have this in terms of vectors. Okay, so if you do Q cross R, or sorry, V cross R, what do you get? Well, what is the magnitude of R? What is this?
Hypotenuse.
What's the hat? What kind of vector has a hat? Unit vector. What is the magnitude of a unit vector? 1. Okay? So if you take the cross product, this becomes V times 1 sine theta. So this R is a placeholder. What does it tell you? The direction. Only the direction. The magnitude.
So here we're just going to try out how to calculate a magnetic field. And remember, just like when we're calculating an electric field, we're just plugging this into our field equation. In this case, our field equation is going to be Biot-Savart. But let's start by looking through the problem. So we have a proton, and here's our proton right here. We know this is E, it's plus. This is 1.6 times 10 to the negative 19 coulombs. It's moving along the x-axis with a velocity equal to 1.0 times 10 to the 7th meters per second. When it passes the origin, we want to know what's the magnetic field at these 3 different points. So we're going to start by drawing a picture, and we want to start with this 3-dimensional axis. So essentially what we're doing is we have this proton moving along the x-axis. So we're going to freeze frame right at the middle. And then we're going to draw, this is its velocity, which we've mentioned over here. So here's our proton. And it's moving along the x-axis. So you have to remember that it's moving. We're just looking at a stopped motion. So it's right at the origin, okay? And now we want to figure out our 3 points that we're going to calculate. And I'll use different colors to indicate the different points. So we're going to figure out position 1. Position 1 should be along the x-axis over here. Position 2 is going to be on the y-axis. And then position 3 is going to be right here. So remember, position 3 is this 1, 1, 0. Actually, we'll do it with the highlighter. So this is 1, 1, 0. Here's our position 1, and here's position 2. Okay, so we're going to calculate all 3 of these. We have our picture. We can draw some little points. So this is in millimeters. This is 1, this is 1, this is 0, and this is our 1, 1. Okay? So 1, 0, 0, 0, 1, 0. These are all in millimeters. Okay? So you want to think about what this looks like. Well, if we're thinking about the magnetic field, before we even plug in some numbers, we know that since we're traveling along this axis, all of the magnetic field lines are going to curl around here. And they should be bigger closest to the actual particle, and they should get smaller out here. So we're going to figure out just the tangent of those. So if you have a magnetic field that looks like this here, you're going to have a magnetic field that points like this here. All right? And so we can expect, before we even get started, that our magnetic field should be biggest here, smaller here, and it should be 0 here. Because we're looking at, this has to be completely perpendicular, and it gets smaller out here. And the magnetic field lines are always going to be these circles. All right, so then we have to go to our equation, and that's the Biot-Savart Law. So Bio looks like this. So B is equal to mu naught over 4 pi. That's like our K from our electric field. Remember, this is a vector, so this is going to be QV, where that's the speed, cross R hat over R squared. And you can rewrite this in a more scalar form by doing the cross product out as sine. Over R squared. All right, so this is our equation from Biot-Savart. Okay, and then we're going to plug in for our different B's. So remember, B1, we know this one's going to be 0, but let's see why. We have mu naught over 4 pi QV sine theta. Well, this R hat, right, our R hat, let's use, what color should we use for R hat? Let's use this color. This is our R. So you know that when you're talking about R and V, the angle between these two things is equal to 0. And sine of 0 is equal to 0. So this becomes 0. So even though we have QV and R squared, this whole thing goes to 0. So that one's pretty simple, and it matches what we think by looking at the visual. For the next one, we have B2. So B2, mu naught over 4 pi QV cross R over R squared. Well, R in this case looks like this. So this is R2, this was R1. And you can see in the case of R2, V is still in this direction, so the angle between these two is going to be a right angle. So when this is a right angle, the cross product goes to 1. So this would be sine of 90, which is 1. So we can plug that in. We get mu naught over 4 pi QV sine of 90, which is 1, over R squared. So now we can actually plug in numbers for this one. Mu naught, I'm just not going to write that out. But we get Q, which is 1.6 times 10 to the negative 19 coulombs. We have V, which is 1 times 10 to the 7th meters per second. And then we have R, which is 0.001 squared. Okay, I'm going to move some of this stuff up so we get it out of the way. And you can see mu naught, just for reference, is equal to 4 pi times 10 to the negative 7th. I think it's Tesla meters over amps. Yeah, Tesla meters over amps. So when we plug all this in, we end up with 1.6 times 10 to the negative 13 Tesla. Because we're doing a cross product, if you want to do this as a vector, you're doing basically a cross product of x hat cross y hat. For those of you that remember vector calc, this is 1.6 times 10 to the negative 13. Tesla in the z hat direction, or sometimes k hat, depending on what notation you're using. So there is that. This is our first one. And then last but not least, we have B3, which is mu naught over 4 pi QV cross r hat over r squared, where V is the same. The only thing that's different here is now R3 has this angle of 45 degrees with V. So you end up with mu naught over 4 pi. We still have the same Q, 1.6 times 10 to the negative 19 coulombs. Oh, we're running out of space. V is 1 times 10 to the 7th meters per second. This is going to give us sine 45 degrees, because that's this angle right here, divided by r squared. Well, that's this. We use Pythagorean theorem, and that gives us square root of 2 millimeters. So times 10 to the negative third gives us meters. We square that. And when you plug all this in, it gives you 0.57 times 10 to the negative 13 Teslas in the z hat direction again. Because if you look, if you use the right hand rule, this guy crossed with this guy should still give you something in the z direction. And that's just because these two vectors lie in the xy plane, so the answer is always going to be perpendicular. All right. And we also just know, because this thing is part of this tangent to this circle, it should point out like that as well. So that's our final point. You can also write this as k hat. And now we have all three of our answers from the Biot-Savart Law.
What's the source of electric fields?
Charge.
Charge, right?
Yeah.
It doesn't have to be stationary charge, right? Moving charges also create electric fields. We're going to be kind of ignoring that for a while, just because we're going to be focused primarily on calculating the magnetic fields, okay? But any charge creates an electric field. Moving charges, however, can also create magnetic fields. And if the charge isn't moving, you definitely don't have a magnetic field, okay? So moving charges create magnetic fields. And this is the law that dictates what one moving charge creates as a magnetic field. It's called the Biot-Savart Law. It's spelled Biot-Savart, okay, because French stuff. It's sort of the magnetic equivalent of Coulomb's law, okay? Remember, in the first couple chapters, we spent all of our time trying to figure out how to calculate electric fields, and either through integration, through Gauss's law, starting from potential, okay? So that's what we did in the beginning. Then we've applied electric field to applications like circuits, okay? So that's what we did in the next 3 chapters. Now we're switching over to the M part of E and M. This is the magnetism part. And of course, magnetic field is represented by a B for magnetic, which doesn't make a whole lot of sense, but maybe it does in French. But here, but I think that's actually not a joke. I think this is actually where the B comes from. But mu naught over 4 pi, this is QV cross R hat, okay? So this is a cross product, meaning the plane created by the vector that connects the moving charge to where you want to figure out the magnetic field and the speed, the velocity. There's a plane. That means the magnetic field is always perpendicular to that plane. That's what the cross product tells us. So the more perpendicular these two vectors are, the closer the angle between them is to 90, the bigger the magnetic field. What happens if you're along the direction of travel? What happens if your R and V are parallel?
0.
0, okay? So we did an example where we talked about how if you have something moving along the x-axis, a positive charge, right? You'll get a magnetic field in the YZ plane, right? But you're not going to get one along the x-axis. If you're looking for a magnetic field along the x-axis, 0, you have to be off axis to get a magnetic field, okay? So I'm going to try another problem.
Okay, so here we have two charges again. They're traveling in the same direction with a speed of 30 meters per second. So we can sort of recreate that. These little guys are traveling like this across, and we're taking a snapshot when they're right here. So that looks like that. We know they both have this same speed, and that speed is equal to 30 meters per second. They each have their own charge, so we'll figure out using Biot-Savart again. Remember, Biot-Savart is this. We need to figure out as a vector what these are going to look like. And so because we know the direction of travel, we also have to keep track of which direction the R is. So for 1, this is R1, it's the distance to the origin. This is R2, also the distance to the origin. Remember, this is our origin here. And we're trying to calculate the magnetic field at the origin. So we're really calculating two magnetic fields. We'll be calculating B2 and B1 because we have two different charges and we can calculate two magnetic fields and add them at a point. That's called superposition. So that will be B total at origin is equal to B1 plus B2. And remember, all of these are vectors, okay? So we're going to calculate our B1 and B2. We'll start with B1. So B1 is equal to mu naught over 4 pi Q1 V, which is the same for both of them. Now the cross product, we have 90 degrees here. So this is going to be sine of 90, which is 1, over over R1. Okay. Now, if you want to use right-hand rule, you point your index finger in this direction, you point your middle finger in this direction. Make sure these fingers are at a 90-degree angle from each other. So index finger goes in the direction of V. Your middle finger goes down, and that means it forces your thumb, if you're doing this correctly, to point into the page. So we know this will be into page from right-hand rule. Okay. Now that's going to be negative x, so you could call that negative x hat if you want. Not negative x, sorry, negative z, so you can call that negative z hat if you want, but you can also write into the page. So this is going to be 4 pi times 10 to the negative 7th Tesla meters over amps over 4 pi. Q1 is 8 times 10 to the negative 6 coulombs, that's 8 microcoulombs. V is 30 meters per second. R squared, that's going to be 0.02 meters squared. So we put all that into our calculator, and we end up with 6.0 times 10 to the negative 8 Tesla into page. So that's B1. All right. B2, we do the same thing, but we plug in different values. So that's Q2 V, still sine of 90 degrees. So that's going to give us not 0, but 1, divided by R2 squared. So that's 1 times 10 to the negative 7th Tesla meters over amps. You can see we simplified the 4 pi divided by 4 pi. That's going to be 1 times 10 to the negative 6 coulombs, 30 meters per second, divided by 0.01 meters squared. So we plug all that in, and we end up with 3 times 10 to the negative 8th Tesla. And this one, if you do right-hand rule, you point your index finger this way, your middle finger this way, make sure those fingers are at a 90-degree angle, and your thumb comes out of page, or in the positive x direction. So this is going to be B2 as a vector. So now we have B1 and B2, but what we really need is B total, which is B1 plus B2. So which one of these is going to be bigger? Well, 6 times 10 to the negative 8th Tesla into the page is bigger, so we expect our final answer to be into the page. That one's going to win. So we could call this one, if you wanted to be more formal, you can call this one negative z hat. You can call this one positive z hat. So now you have 6 times 10 to the negative 8th Tesla times negative z hat plus 3 times 10 to the negative 8th Tesla z hat. That's going to give us negative 3.0 times 10 to the negative 8th Tesla in the z direction. So that is our final answer. And we have to think, does this make sense? Well, it's not super easy to guess because this charge is closer, but this one is bigger. So we can see when we do the math that this is going to give us the larger field, and so therefore that whatever direction we get from this guy is going to win. Okay, let's discuss this. Okay, better. It's like, okay, let's talk about this. So, which way do you point your thumb? Out of the page, right? That's the direction of motion of a positive charge. So the positive charge goes out of the page, which means you curl your fingers like this. So the magnetic field lines should look like circles going this way, okay? So that's going to be counterclockwise. So you'll have circles going this way, which means at this point, the tangent to that circle points down, okay? So that means the magnetic field at that point, the vector should be down, all right? Okay, let's try with a negative charge. So what happens to your magnetic field when you're moving with a negative charge? Now, a positive charge we know follows the right-hand rule. A negative charge kind of follows, I don't know, what I would call maybe like the left-hand rule. If you use your left hand, it's always going to work. The main thing is you want to remember that these magnetic field lines are going to go around like this, and they're going to get smaller out here, but they're not going to, so they're going to go over this way and behind this way. So this, at these points, you want to figure out what it's going to look like. And if you're at A, for instance, at this point, the tangent of this, if you do V, that's your index finger, cross R, that's going to point towards A. That's going to give you something that's into the page. But because this is a negative charge, if you're doing it with your right hand, then you know it has to be just the opposite. The other option is, so this A is out of the page. The other option is to do this with your left hand. So your left index finger goes this way, left middle finger goes this way, and that's going to cause your thumb to point out of the page like we already found. So we're just finding tangents of this circle. For B, we can follow the same procedure. We have our V going in this direction. Oops. So left index finger, then we have middle finger, left middle finger, and that's going to give us a vector that points into the page. You can draw this like this tangent, or you can draw it like this, and here this is like this. Okay. At C, we also have into the page. It's the same essential idea. We have V, this is your index finger. We have R, which goes this way, so V, R, but these are still going to be in the XY plane, and so your field has to point either into or out of the page. If you use the left-hand rule, it's going to be into the page, or sort of like this, okay? Last but not least, we have D, which is directly above, and if you look at the way this is going, this is our electric field line. They should be going in these circles around like this. So here, this should give us something up.
Oh, yeah.
So we have this Biot-Savart Law. We can rewrite it for current, right? Because remember, Biot-Savart is just a moving charge. If you have a bunch of moving charges, you can call that a current, okay? Well, let me show you how that works. So B is equal to mu naught over 4 pi, Q V cross R hat over R squared, okay? How do we rewrite velocity? What's another way to write velocity?
Speed.
As a derivative, maybe?
D X. Yeah.
Distance over time.
Yeah, ds dt. Okay, so let's say we write this as dB. Okay, so now this is mu naught over 4 pi dq, just for any little small charge. Now we can write v as ds or dx or dy or dz, right? dt. That's still velocity, yes? Okay, and there's your vector. So this is a cross product with r hat, still over r squared. Okay? Well, you can just shuffle these around, turns out. And what's dq dt? Current. So this becomes mu naught over 4 pi dq dt, which is current, ds cross r hat over r squared. Okay? And so that's what this is, which is basically the exact same thing as the Biot-Savart Law we already talked about, just written in terms of current instead of charge. And the only real thing you have to be wary of is, what the fuck is ds?
A very small length of wire.
A very small length of the wire, right? Which direction is the vector?
Same direction as current.
Same direction as current. Okay. Oh, did you read that?
Context clues for the win. We can pretend like I'm smart.
Very good language skills. All right. So this is the magnetic field created by a very short segment of the wire, which is basically the same as the magnetic field created by a moving charge. That's a single point. Okay. So we're just going back and forth. But this is a little bit more practical because usually we don't just have one moving charge, we usually are creating magnetic field with the currents. So we want to actually have the whole current. Okay? Fun fact, now that this is dB, what do you think we're going to do with it? Yeah, because we don't usually care about just a little chunk of the current, we care about the whole current. So we have to add up all little chunks to get the total magnetic field. Okay? So, yeah. Once again, we draw our picture. You need a coordinate system. You need all your currents and or moving charges. You want to identify where you want to calculate the magnetic field. Then you determine the direction using right-hand rule. You write the Biot-Savart equation, and you integrate. Okay? So remember all those integrals we did for electric field, all those integrals we did for electric potential. It's the same technique. The only difference is it's still a vector, but now it's a cross product. So the sine cosine thing gets a little bit different. Remember when we did electric field, we had to figure out the sine and cosine to get the different vectors. Okay, x and y usually. So that's the only thing that's changing. But the whole technique of using density and figuring out what dq is, all of that stays the same. Okay, and so I'll walk you through a standard one. All right.
So here we have our infinitely long and straight wire. And obviously it's pretty hard to draw this as infinite, but it's laying along the x-axis. We want to know what the magnetic field is at P, and we also know that this wire has a current running in the positive x direction. So before we even get started, we want to figure out what our magnetic field is, and we know that magnetic field comes from Biot-Savart Law. And the Biot-Savart Law says B is equal to mu naught over 4 pi. In this case, this would be I L cross r hat over r squared. If we want this to be the infinitesimal form, because we want to draw this out for each little point, we want dl dB. And what that means is we're going to break up this wire into a bunch of super tiny pieces of the same size, all ds, and in this case it's going to be dx, all size dx, and dx is a vector in the direction of the current, which points in the positive x direction. Okay, so instead of dl, sorry, this is dl, we get dx. The other thing we want to remember is for each of these little guys, let's draw another one. Let's say here's our little dude. Okay, for each little guy there, we have our current, which points in this direction, and then we have our R, which points in this direction, and that leaves us a theta, which looks like this. So this is going to change because if you go over here, you can get a different dx, which has a current that's the same, an R that's a little bit different, and a different theta. So we want to set this up to add up all of these little pieces and get the B dB, which is the sum of all B. So we sum up all the dBs to get the total B at this point. Now we want to figure out the direction, and using right-hand rule, you can see I, if your index finger points this way and your middle finger points this way, that creates the xy plane. It doesn't matter that the angle, just for the direction of the magnetic field, it doesn't matter what the angle is. That'll matter for the magnitude. But that's going to give us a B that points out of the page. So each dB is going to point out of the page. So we know when we sum all dB, they all point out of page, which would be the positive x direction. I mean, not x, positive z direction. All right, so we have our direction. Now we're just going to worry about the magnitude. So we can rewrite our Biot-Savart law to be dB is equal to mu naught over 4 pi I dx sine of theta over r squared. So just to sort of keep track of everything, here's our dx. I can get rid of these so they're not confusing. Oops. Oops. Well, we'll leave that one there, I guess. Here's our sine of theta and our r squared. So this is just the magnitude, and in order to get what we need, we have to integrate this from negative infinity to infinity. But going over here, we know what I is. We're given I. Dx is just dx in this case, but we do have to worry about sine of theta. Now sine of theta, remember this length is d, so the sine of theta should be d over r, and we know r is going to be equal to square root of x squared plus d squared, because this distance is x, right? It's also this distance. It varies. That's why we use a variable to describe it. So we get d. Okay, if we want to figure out our angle, that's this theta. That's going to be over here, right? Let's use this triangle because it's a little more obvious. This is our x. But it works over here when the angle gets weird too. This is our x. And remember, we know it changes. So it can be over here, it can be over here, it could be over here, okay? But over here, here's our d, here's our r, here's our x. We can use what we know about right triangles to give us d over square root of x squared plus d squared. All right, we know r is equal to x squared plus d squared. So when we plug back in over here, we can pull out current because that doesn't change. We end up with d, and I know that's kind of an unfortunate choice of variable, and I'm sorry. That's going to be d over square root of x squared plus d squared times 1 over x squared plus d squared, where this is r and this is from our sine of theta. Okay, and we still have a dx, and now we're ready to go. We can just simplify, so we get mu naught I over mu naught I d over 4 pi. This is going to be dx over x squared plus d squared to the 3/2. And we can bring this back up over here. Let me just mark this so you guys remember what happens here. And this is our r. Okay, so we end up with mu naught I d over 4 pi. This gives us a very nice d squared x squared plus d squared from negative infinity to infinity. And that's going to give us mu naught I over 4 pi d, because you can see this is going to cancel, and then this is infinity over infinity minus negative infinity over infinity. So this whole thing is going to give you 2. So when we simplify that, That's going to give us mu naught I over 2 pi d. And that means B for an infinite wire is going to be mu naught I over 2 pi, I guess we'll call it R, and that's going to be, in this case, out of the page, but this is the more general, this one's out of the page. But in general, this is the magnitude of the magnetic field from a wire. And we didn't go through all the math here, but if you look at this, this is clearly a trig sub. But remember, this is not a math class, so if you want to remember how to do a trig sub, just look it up.
I like the connections though. Alright, so let's try this one out.
So this is our first C. First one of this might be the right answer.
C.
There's no way you could ever know this.
It's not C.
Well, damn. Our dreams crushed.
The counterclockwise clock. Mostly I just have it because it makes people really angry.
One of my math teachers
Like
had
a
a
real
unit
thing,
circle
like,
as his clock.
Yeah?
Maybe counterclockwise.
I had my math teacher that was like 1,000 years old thought it'd be fucking funny to put a clock on the wall, but instead of numbers, it was just like insanely hard math questions. It was like, it would like give you the answer of the number, but it was like, what the fuck, why? It was like, what time is it? He's like, oh, it's 4 pi over square root of 2 minus 6. I'm like, what the fuck
Alright.
is that? So we're never getting out of it.
Okay, it's not C. Let me just put it that way. It's A or B. So please discuss and we'll vote again.
You look at the way
I
it's
gotta disagree.
That's fine.
this way.
You're just
like,
wrong.
If you go to the left side, right, and you go inward, right, so then the direction is going so kind of
So look at
Okay, so look at the far right curve, right? It curves inwards, and so your thumb is pointing towards you. And if you continue in that line, it goes clockwise, right?
Okay.
I may be fucked up right here, but
I thought it meant, oh, I thought it meant like,
I don't know.
I thought it meant like around the loop, like this way. So that's what I put kind
I thought those lines were
Okay, so that's
the
gotcha.
the field.
Yeah, okay. That's why I got confused.
Right? Maybe?
Maybe not. We'll see. Fuck it, I don't know. One more person.
Oh shit. Yes, better. So it's gonna be clockwise. And here's where the right hand rule starts to really anger people. Okay? So what's the shape of the current? A circle. What's the shape of the magnetic field lines? Technically also a circle. Okay? So it's circles that create other circles. So you have to be careful. It turns out the right hand rule can go both ways. If you point your thumb in the direction of the magnetic fields, it creates a circle for the current. Okay? So that means the current goes clockwise. But you can also test this by pointing your thumb in the direction of the current, which means inside the loop, you should go down. Outside the loop, which way do you go up? I almost said up.
Yeah, that was like,
Up,
spoiler.
right? So basically, on this side of the loop, you have a magnetic field that goes like this. So it goes in through the loop and then out and then comes back through. And as you go all the way around, right, it's gonna go around in circles around the circle, which is a little bit crazy. But basically, right-hand rule with this curling thing works both ways. If you pick a part of the current, you can figure out where the magnetic field loops around the current. If you put your thumb in the direction of the magnetic field, you can figure out which way the current goes. Okay, so it's actually fairly robust, but you have to be able to visualize this to understand what's going on. This circle creates a bunch of other circles. Okay? What? It's like this infinite thing that goes on. Yeah. So let's talk about the magnetic field due to a loop of current. Oh, but one thing I want you to notice is where is the magnetic field going to be the strongest for the loop?
Inside the loop.
Inside the loop, because all the lines outside, right? If there's 5 lines going through the loop, then there's lines outside that are distributed over a larger area, a larger volume. So the density of the magnetic field drops off significantly outside the loop. It's pretty dense inside the loop. So the primary magnetic field that we'll be able to use is going to be inside or near the inside of the loop. Okay, so even though there are still magnetic field lines outside the loop, they're not as important as the ones inside. All right, so let's talk about the magnetic field in a loop of current. So inside the loop, right, because we have this situation where this points out, it's actually just going like this, right? The lines come out and they go back in on the outside of the loop. So if you look at the cross section of the loop like this from the top, you can see this gives you the magnetic field inside the loop, but of course magnetic field lines are also loops, so they change direction as you go outside the current loop, okay? So here's this loop from the side. And what does this actually look like?
Magnet, bar magnet.
Yeah, it looks a lot like a bar magnet, but instead of the bar magnet, remember, was sort of set up this way, right? And so you would go north to south. The loop is a little bit different shape, but you're still going north to south. Inside the loop, it goes from south to north. Okay, outside the loop, it points from north to south. So you want to think of a loop of current as a bar magnet, and it turns out a loop of current is actually something called an electromagnet, okay? Because the easiest way to create a magnetic field is actually by running current, not by finding a material that has magnetic properties and making sure that all the magnetic things line up, all right? So we're mostly going to define loops of current as bar magnets. So which is the north pole of this loop of current? Right or left?
She said north.
Center.
She said
So we're one of these is north, one of these is south.
The right.
Which one's north, which one's south?
The right.
The right side should be north, because remember, the magnetic field lines, if this is the magnet, point from the north side back to the south side. Inside the magnet, they go from south to north. But basically, if you put a bar magnet with the north side here, it would look just like this. Okay? If you had a long, smushy one.
Smushy.
Yeah,
Physics
that's a very technical
It
physics
is
term.
smushy.
Okay? So, if you want to look at this, all right, here's the magnetic field approximately from this loop. Obviously, it loops back around, but we're ignoring that. Okay? What does the magnetic field line look like here? It points this way and goes around this way. So what happens if you put this next to this? They're going to repel, because this is the north pole of this electromagnet. This is the north pole of this bar magnet. If you put a north pole and a north pole together, they repel. Yeah. Okay, so force happens. All right? So if you look, this is what I mean by smushy bar magnet. Right?
Oh.
So north is on this side, south is on this side. The magnetic field lines look the same. So a current through a loop of wire behaves a lot like a permanent magnet that's a bar magnet. Okay? Okay. So,
A hot dog.
this is the same thing we just did.
Hot dog.
So fun fact,
Hot dog.
if you hang a loop of wire with a current through it, if it's hanging from a string and it's free to rotate, where does it rotate?
What the word?
The north pole of that loop, right? This side of the loop points that way, because it works just like a compass. If it's free to rotate, it's going to point towards geographic north. All right. So and this is we're talking about a loop of wire, but usually when you make an electromagnet, what does it look like? Coil of wire, right? Which is just more loops, which means every loop gives you a certain amount of magnetic field. So if you want twice that, 2 loops. If you want 10 times that, 10 loops. Okay, so it looks something more like this. This is an electromagnet, all right, and this is one in use.
Oh.
Okay, so when we do like recycling from garbage and you want metal, you get a big electromagnet. The metal that you want to recycle sticks to the magnet. And like now we have a bunch of metal, take it over here, turn it into new things.
How far do you have to be for it to light your debit card?
Well, it drops off in the inverse square, so you have to actually be pretty close depending on the size of the magnetic field. But I wouldn't take my cards in there. Yeah. All right, just to be safe. So here's the question.
Oh, for fuck's sake.
Okay, so the North Pole is on the bottom because remember, inside it points from south to north, outside it points from north to south. So this would be the North Pole, this would be the South Pole. Okay?